all of you know, the semester is coming to an end. Actually, year 2025 is also coming to the end, okay? Which means Christmas is coming, which means winter section is coming, and which means Chinese New Year's is coming. As I understand, this year's winter sections is 2 months long, okay? So during such a winter section, I hope you have a very good break, okay? You can relax and enjoy your life, okay? The reason I'm saying that is, pressure is usually building up at the end of the semester. But if you, including myself included, if I have something to look forward, then the pressures may be less stressful. Okay, let me put it this way. All right. Okay, let's go back to spectrum. System spectrum actually tell us how the system modify the input signal spectrum. So this is the role of the system when in the context of frequency domain. Now, a tool for such a so-called frequency domain modification is an equalizer, audio equalizer, okay? I think you also something similar before, which means you can, by adjusting these buttons up and downs, okay? You can actually adjust the frequency response of the system, okay? For example, you want to attenuate a particular frequency, or you want to boost a particular frequency band. You can do that by using an equalizer, all right? And I'm pretty confident that many of your music players in your mobile phone has such a function, all right? Now, let me shed some light on the property of system spectrum, okay? A system revise or modify the spectrum of the input signal. Now, I can do it in 2 general ways. The first is I can perform low-pass filtering, which means the frequency response of system, amplitude response of system looks something like this, okay? Now, if that is the case, this is what I will get, okay? Well, the original signal is the blue line, and the low-pass filter signal is the red line. By comparing these 2 curves, it is easy to see that low-pass filtering isolate the global trend, okay? So the low frequency, which means the low frequency band components represent the global, the general trend of the signals. Now, if this is the amplitude spectrum of a low-pass filter, then the amplitude spectrum of a high-pass filter will look something like this, all right? Now, if I perform high-pass filtering, okay, one way to do that is first, I perform low-pass filtering. So the high-frequency components will be filtered out. So the difference between the original and the low-pass filter signal become the high-frequency components, which is the residues of the low-pass filtering operation. So this represents the high-frequency components of the original signal. From this result, it is evident that high-pass filtering highlights local details. Okay. So one is to visualize the system by inspecting its global trend, okay, basic variation patterns. But the other is emphasis on details, on local variations, okay? Which one is more important? It depends, okay? It depends, all right? But that gives you a picture of the frequency, the role of frequency components in different frequency band, okay? Now, the next thing I want to do is I want to introduce you a tool which is called the body diagram to help us analyze system spectrum, okay? Now, body diagram use log, okay? Now, again, this is a linear block diagram for a linear time invariant continuous system with input F and output Y. And we all know that by taking the the Fourier transform of the differential equation, this is what I will get in the frequency domain. Again, let me say it again. This is a beautiful result. And we all know that this equality holds for the amplitude spectrum. And this equation is true for the phase spectrum. Now, the difference, as I mentioned before, this involves addition. This involves multiplication. But if I take the log of this equality, this is what I will have, okay? Now, after doing that, what I have here is no longer addition, multiplication, but addition. We all know that addition is simpler than multiplication. And that is what body diagram is all about, okay? That is, when dealing with amplitude spectrum, body diagram always take log because it want to simplify its mathematical operations. Now, such a simplification is very important. Let me show you why, okay? Now, here, this slide illustrates 4 basic forms of transfer function, okay? Now, I will talk about them one by one, okay? But first, okay, here something is unfamiliar to us. That is, why is this a quadratic factor, all right? It is actually not complex at all, okay? We all know that this transfer function, this representation, is a transfer function of a standard spring mass damper system or standard second order system, where omega n represents the natural frequency and eta is the damping ratio. If I want to go to the frequency domain, I need to replace x by j omega, and this is what I will get, all right? When I go from here to here, the only thing I do is replacing x by j omega. Please wake up, okay? Okay. And then what I will do next is I will divide everything by omega n squared, okay? So after dividing everything by omega n squared, the numerator changes from here to here. Same thing happened here to here, all right? And this factor become this, and this term become this, right? And this is exactly what we have here. This is this. This term is this term. 1 is, of course, always 1, all right? Okay, so this is another way to represent a quadratic factor, which means, okay, now, one important thing of such a representation is that here we don't directly deal with frequency. That is, if I want to looking into the impacts of the frequency, how the changes in frequency, how the change in frequency alter the spectral properties of this factor, I look into this normalized frequency, which is omega divided by omega n. I don't deal with omega directly. I deal with omega, this ratio, which is the frequency divided by the natural frequency of this second order system. Now, why use logarithmic function? Why do I use log function in the body diagram? Here, this is a general representation of any arbitrary transfer function, all right? KP represent again. This means that we have two sample zeros. This term means that I have m poles located at the origin. This term means I have m distinct sample poles. Okay, and this means I have r pairs of complex conjugate poles. All right, so no matter how complex a transfer function is, it is actually made up of many fundamental factors, okay, which include, again, integral and derivative factors, okay, first order factors and quadratic factors, okay. Remember, please be aware that these exponents can be minus or positive, all right? So the good thing of using log is if I take the log of this transfer function, this is what I have. Now, and then due to the nature of log, I can take each one of them apart. And then by understanding each of these components, I can summarize their overall impacts by simply acting them together, all right? Okay, I will demonstrate how it works in the later part of today's course. But let's first look at the examples, okay? That is, I want to study these terms one by one. The first thing we want to do is go back to the first order system, okay? Whose differential equation is this. Here, I assume zero initial condition, and we all know that its state response is this. And we just saw in the previous lecture, less than 50 minutes ago, the transfer function of this system in the frequency domain is actually this, all right? Now, since we are dealing with body diagram, we use body diagram to describe the frequency response of the system. The first thing I need to do is this, okay? I take the log and times it by 20 to determine its, to illustrate or describe its frequency amplitude spectrum, okay? And this is what I will get, all right? And since it's in the denominator, when I move it to the numerator, okay, I will have a minus 1 over 2, all right? So And if I move this minus 1 over 2 outside this log, this is what I will get. All right. Now, here, what I want to do, as illustrated by the title of this slide, is that I want to establish the asymptotics of this spectrum, of the spectrum of a first order system. Okay. Now, to do that, let's first assume omega is very, very small. How small is small enough? Well, in this particular case, it depends. And in this particular case, omega is very small if it is much smaller than 1 over tau. Why is that the case? Because here we have a term, omega over tau. If omega is equal to tau 1 over tau, then the product of omega tau is, of course, 1. However, if omega is much smaller than 1 over tau, then this product will be very, very, very small, because it will be much smaller than 1. And if you put such a number next to 1, then it becomes negligible, right? Because when omega is much smaller than tau over 1, omega tau is much smaller than 1. So compared to 1, this becomes negligible. And this is exactly what we have. What we have here, remember, okay, I should mention that once you take the log and you times it by 20, its unit becomes dB, which is decibel, all right? So that is one extreme case. Let's go to another extreme case, because we want to establish asymptotics. That is, we want to know what will happen to this when omega is very, very large. How large is large enough, again, compared to 1 over tau? Because as I said, as we just saw, we are dealing with omega, the product of omega tau, okay? So if omega is 1, tau 1 over tau, okay? Then this number is 1, this product is 1. However, if omega is much larger than 1 over tau, apparently the product of omega tau will be much larger than 1. Again, when you put such a number next to omega 1, okay, and since in this case it is much larger than 1, then this becomes negligible. We can just ignore it, okay, with minimum inaccuracy. All right. So this is what I will get after omitting 1. All right. And what is this anyway? Okay. If you put these two things together, the asymptotic of the amplitude spectrum of a first order system actually looks like this. Okay. This, of course, corresponds to this. And this comes from here. Okay. Now, what is the slope of this line? Okay. Now, the first thing that we need to know from this figure is that this figure, when it comes to the asymptotic of the amplitude spectrum of this first order system, the critical frequency is 1 over tau. Okay. Of course, it is 1 over tau, because this is actually the boundary that will separate the frequency domain into two distinct portions. All right. Now, so it is located. This turning point, this critical turning point, is located at the frequency of 1 over tau. All right. Now, to understand, to know this, to figure out the slope of this line, what we need to do is let's just pick any arbitrary two frequency. Let's say this is omega 1 and this is omega 2. Okay, and we use this equation. And then we want to know how these two values, what is the difference between the values, the value of this number correspond to these distinct frequencies. One is omega 1 and one is omega 2. Let's check out their difference. Okay, now by using this formula, this can be rewritten like this, and this, of course, can be rewritten like this. Okay, now the difference between these two is actually this, right? Let's assume that omega 2 is 10 times larger than omega 1. Okay, and this is what we have. Okay, and here the number comes out to be 20 dB. All right, remember that omega 2 is 10 times larger than omega 1. All right, it means it has a system of a slope of minus 20 dB per decades. All right, which means if what does decade mean? Okay, when it comes to time, we have years, we have century, and century means 100 years, and decades means 10 years. 10 years of time, all right? And minus 20 dB per decade means that whenever you increase the frequency by a factor of 10, is decibel value reduced by 20, all right? So this is a curve with 20 dB per decade slope, all right? All right, this is the asymptotic and exact amplitude spectrum of a first order system. As you can see, they are very, very similar, okay? Especially at the two extreme ends. And we all know that because, and this is something we expected. Why is that the case? Because if you go back to this mathematical derivation, you will know that the inaccuracy of the asymptotics occurs at the critical corner frequency or turning point frequency 1 over tau. Okay, now that's for first order system. Now let's switch to second order system. All right, now for second order system, there are basically two possibilities. The first possibility is look like this. That is, I have two distinct poles, which are all real numbers. Okay, here, okay, let's first not discussing repeated poles. Okay, if this is the case, what will happen is that I can view my transfer function as a product of two transfer functions, G1 and G2. Okay, now when I want to know the decibel value of the transfer function, this is what I do. Okay, and we know I can add this to get this. All right, now remember that here what we have is two first order systems. Okay, and each of the first order systems has such an amplitude spectrum pattern. So let's assume the amplitude spectrum of the first transfunction is this, all right? And let's assume the amplitude spectrum, the asymptotic of the amplitude spectrum of the second transfunction is this, okay? Then the asymptotic of the second order system with such a result is, of course, this. Where do this result come from? Easy. I simply use this equation. That is, I add this curve with this curve, and the sum is this curve. All right. I simply add them together. All right. Here is 0 dB. 0 plus 0 is still 0. All right. Now, in the beginning, this slope is minus 20 dB per decade. But for this part, the slope of this portion of the amplitude spectrum is, of course, minus 40 dB per decade. All right? So this is the very reason why we want to take log. Because after taking log, when analyzing the amplitude spectrums, you can use this result to visualize what will happen if you, let's say, introduce a new component into the system. Because all you need to do is to understand the amplitude spectrum, okay, of the new component. And by acting this amplitude spectrum into the original system, you can easily visualize what will happen, all right? Okay, because of what? Because of addition. If it is multiplication, such a visualization will be much, much more difficult, all right? Now, let's go back to second order system. Now, for this second order system, I assume I have two distinct poles. But here, I assume I have an underdamped system, which means I have a complex, the pair of poles that I have is a complex conjugates. And we all know that the transfunction of a standard second order system can be written as this. So this equation simply take the amplitude of this transfer function, okay? I don't want to go through the mathematical details, but all the mathematical information for the derivation are all given here, all right? So this is the amplitude spectrum for this underdamped second order system, and this is its phase spectrum, all right? Now, again, when you look at the frequency omega does not stand alone. It always appears with omega n to be more precise. It always appears as a ratio of omega to omega n, all right? So natural frequency really matters. Now, I can plot this out by using different values of omega by omega n, and this is, okay? Once I do that, the magnitude of the decimal value of this actually do something like this, which means it will have a peak. And this peak is what we call resonant peak, all right? Now, it can be shown that if the value of the damping ratio is between 0 and 0.707, then the value of MPW, that is the value of the resonant peak, okay, which is defined like this, where omega R is the resonant frequency, okay? Omega R is the resonant frequency. And here, the horizontal axis corresponds to U, is U, where U is the normalized frequency. That is the ratio of the frequency to natural frequency. And this is the amplitude spectrums of the standard second order system. The reason why we have a family of curves is because damping ratio is another parameter that we need to take into consideration. Okay, so as you can see, when the damping ratio becomes smaller and smaller, the peak, the resonant peak, become more distinct. Okay, more pronounced. Okay, now this is phenomenon which give us an impression that here we have peak, or we have a thing similar to overshoot. Okay, what is an overshoot? Okay, let's review the unit step response of underdamped second order system. Here, what we are pay attention to is percent overshoot. Okay, now this is a standard curve for unit step response for a second order system, and this is overshoot. And the percent overshoot, as we derived before, is this. All right, okay. Now, as you can see, there are some similarities between this overshoot and this resonant peak. Note that this is the result presented in the time domain. This is the result appear in the frequency domain. Okay, time, frequency, different things. Okay, but even that in different domain, one in frequency domain, one in time domain, we still see their link. Okay, because here, as we saw before, percent overshoot only is determined by damping ratio, and it only depends on damping ratio. Okay, and the larger the damping ratio is, the smaller the overshoot. Same thing happened here. The resonant peak only depends on damping ratio. And as you can see from this family of curves, the larger the damping ratio, the smaller the resonant peak. Okay, so this is what we saw before. This is damping ratio, and this is percent of overshoot, which this curve, of course, is determined from these equalities. From this equality, all right? Apparently, as omega increases, percent overshoot decreases monotonically. Now, okay, that for this is for the amplitude spectrum. For the phase spectrum, based on this result, I can plot phase spectrum for a standard second order system. Okay, again, here we have a family of curves because here we treat eta as an additional parameter. All right, let's check out the example. Hopefully, with an example, we can understand body diagram to understand system frequency response better. Okay. Here, this is a system whose transfer function is x plus 0,1 divided by x plus 5. Since we want to study system spectrum, so we go to a frequency domain by replacing x with j omega. All right, and then by finding the amplitude and the angle of h j omega. Remember, this is a complex number, and this complex number, when presented in the complex space, it has its polar coordinates. This is the distance to the origin, and this is the angle respect to the horizontal axis. All right, and this is what I will get. All right, if I plot this as a function of omega, this is what I will find. Okay, now similarly, if I plot this function out by substituting omega with different numbers, different values, this is what I will have. Now, with this in mind, and recall that when we have a sinusoidal input, okay, the steady state response of a linear time invariant system will look like this. So if this is the case, the question is, what will the output of the system be if the input signal is a sine wave with a frequency of 2 radian per second? That is omega equal to 2. When omega is equal to 2, the amplitude of the transfer function is actually 0.372, and the phase is 65.3 degrees. All right. So based on this result, okay, the numbers are all given here. The output should be this. Okay. The output will always be also a sinusoidal signal with the same frequency, right? But the amplitude now is now times by 0.372, which is the value of the amplitude spectrum of the system at omega equal to 2. Now, similar thing happened to the phase spectrum, all right? So the next thing we want to do is we want to study the system spectrum of many center simple system, okay? The first thing we want to study, the first simple system is a system of time delay, all right? So this is a system, and the only thing it does is to delay the input signal by t, all right? Where t can be t seconds, all right? Now, for such a time delay, its Laplace transform, we have shown that is this. Remember, in the x domain, what we usually see is something like this, okay? We see a ratio, and in such, we see ratios, and in such ratio expressions, the denominator and the numerator and the denominators are usually polynomials of s, right? Whenever you see exponential function is in the x domain, it is always related to time delay, no exception. So this represents a system of time delay where the amount of time delay is t time unit, okay? Typically, the time unit is second. But since I want to go to frequency domain, so I replace x by j omega, and this is what I will get. And next thing I need to do is, of course, to determine its magnitude and its angle. That is, I want to know the amplitude spectrum and the phase spectrum of this time delay system. And this is what I will get. The amplitude spectrum is 1, right? And the phase spectrum is minus omega t, right? Okay, all right? Polar coordinate representation, okay? Here, what we have, this is the angle, and the magnitude is 1, okay? Remember? Let's refresh our memory, okay? In the previous lecture, okay? This is our transfer function, which is a complex number, but we don't like Cartesian coordinates. We prefer polar coordinate representation. There are only 2 polar coordinates. One is the distance to the origin, which is this. The other is the angles, which is this. Distance, angles, distance, angles, okay? Distance corresponds to the magnitude. Angles, theta, right? So always 2 polar coordinates, first and second. Same thing happened here. What I have is this representation. What I have for the time delay system is I prefer to use different ej omega t minus, right? So for this part, apparently is 1, right? Nothing comes ahead of this exponential function. If there is anything comes ahead of it, that must be 1, right? And the angle is, of course, minus omega t, okay? All right. Let's go back to time delay. So let's go, the amplitude spectrum and the phase spectrum of a time delay system is actually this and this. And if we plot them out, this is the amplitude spectrum and this is the phase spectrum. Note that the effect on phase is proportional to frequency, right? The larger the frequency, the larger the phase shift, all right? And the slope is from here, is actually minus t. So the larger the time delay, the larger this slope, okay? But the fact remains to be the effect on phase is proportional to frequency. And this is important because I will show you in the later part of this course. This can damage stability. This can create instability problem, all right? Now, let's look at another system. And this system is essentially a differentiator, okay? So its transfer function is nothing but an S, because when you times anything in the Laplace domain with X, it always represents you perform differentiation in the frequency domain, right? Now, since we want to perform frequency domain analysis, we always need to replace X by J omega. And then we look at its polar coordinate representation. Its mag and what it is in a complex plane. This number is located at here, where its distance to the origin is omega, and its angle is, of course, pi over 2, right? Right? Okay. So its amplitude spectrum is this, and its phase spectrum is this. And these are the graphical representations of the amplitude and phase spectrum of the differentiator. Okay. Now, this is very important because the impact on the amplitude spectrum is proportional to the frequency. For differentiator, its impact on the amplitude spectrum is not the same. It depends on the frequency of the input components. Now remember that for typical input signals, it actually consists of many frequency components. But when that signal is being differentiated when in the frequency domain, that means the frequency components of that signals will not be equally treated. Okay, why? Because higher frequency component will receive larger amplification, and vice versa. Okay, now this is not good for a controller design. Now we all know PID control. All right, in PID control, let's say this is a PID controller, and the input is always the output arrow. That is the difference between the input, which is what we call actual output or target output, okay? And the output here, what is being fed back is the actual output of the system. And this is the target output. And in this particular case, the target output is a set point, which means the target output is a constant, all right? And with output arrow here, we can perform the control output actually consists of three parts. One part is proportional to the output arrow. The other part is integral of the output arrow. And the third part is the derivative of the output arrow. The good thing about the derivative of the output arrow is that it provides some information about the changing trend of the output arrow. Is it decreasing? Is it increasing? All right. Is it become larger or is it become slower? And such information matter. Okay. But here, I want to make an important remark. That is, be careful with using D-control. Why? Because D-control amplify high frequency components. All right. So when using D-control, a low pass filter is often placed up the D-controller because the derivative greatly amplify high frequency noise. Okay, it will amplify high frequency proportions. But remember that when in a real world, the signal is always not perfectly clean. More often than not, it is contaminated. And due to the random nature of the noise typically has very rich high frequency components. And those high frequency components, the energy, the amplitude might not be very large. So it is okay for the proportional and integral controller, but it is not okay for the derivative controller because the derivative component will amplify noise, okay? Let me give you a very easy to understand examples. Let's say this is my output arrow. Okay, this is time. This is my output arrow. Okay, let's assume for some reason the output arrow remain to be a constant. All right. Now, let's say this is the node. I'm sorry, different color. This is nodes. So the input of the real input that we send to the controller is not this, but the sum of this and this. So I'm sorry. Let's take a 10-minute break. 今天有